What's up, scholars? Today we are continuing our discussion of proportions and ratios. We're going to do some problem solving in geometry. So let's remind ourselves, what is a ratio? It's a comparison of two numbers and the same units. Comparison of two numbers with the same units. That part is super duper important. They must be in the same units. All right. So to solve a ratio, you're going to get the units to be the same. So convert to same units. And then you're going to simplify or reduce your fraction. Simplify or reduce the fraction. So let's look at some examples. Example A, we've got 3 feet over 12 inches. We've got a comparison of two numbers, but they're not in the same units. So let's make them in the same units. How many inches are in a foot? There are 12. So we're going to match these up so that the units will cancel. So we're going to want feet on the bottom because we have feet on the top. So we said there are 12 inches in 1 foot. We've matched these up so that the units will cancel, which is the whole point of having same units, that the units cancel, because we got the same on the top and the bottom, because a ratio is a unitless quantity. There should be no units when we're all done. All right. We can also cross off those 12s because it's the same on the top and the bottom. So our ratio is 3 to 1 here. Cool. All right, in B, we have 1,000 centimeters to 50 meters, but we know that we have 100 centimeters in 1 meter. And we've organized them that way so that our units cancel. Bye-bye, bye-bye. We have no more units anymore, which we should not. Then we multiply straight across, and we get 1,000 times 1, which is 1,000. 50 times 100 is 5 with 3 zeros. We can reduce that by dividing both of those by what? 1,000, and we get 1 to 5. Cool. All right, let's decide whether these statements are true or false. So if A over B equals C over D, then A over C equals B over D. What did we do? We switched the middle numbers here. We switched the means. Well, let's try our cross product of the first one. So let's do A times D equals C times B. A times D equals C times B. That's for the first one. That's our first cross product. And our second cross product, A times D equals B times C. AD equals BC. Is that the same? Yes. Multiplying, you can multiply in whatever order you want. Right? 2 times 3 is 6, and 3 times 2 is 6, so it does not matter. So yes, they are the same. And here's our proof. We did our cross product. Let's do the same thing again. Actually, you're going to do the same thing again because you can totally do that. So you're going to finish 2 and 3 and show me. So then let's look at some properties of these proportions. We talked about these two in our last set of notes, so let's just remind ourselves here what the cross product property says. It says the product of the means is equal to the product of the extremes. The product of the means equals the product of the extremes. Okay, and that's basically saying if we had A over B equals C over D, then A times D equals C times B. A times D equals C times B. That's what that cross product says. The reciprocal product says if we have one ratio that equals another ratio, we can flip them and their reciprocals will be equal to each other as well. If, let's write it out in example. So if we have A over B that equals C over D, then we can flip both of those fractions and their reciprocals will also be equal. Then B over A equals D over C. Cool. We've got two more. One of them is based off of question 1, which says that we can, in essence, switch the positions of the means and we will get the same thing. So if we have A over B that equals C over D, then it is true that we will get the same answer if we switch the position of these means. So A over C will equal B over D. Cool. And our last one is going to come from what you find when you do 3. So if you haven't done 3 yet, pause the video, go back and do 3. If you have a ratio where A over B equals C over D, you can add any number to both of those numerators. And the same thing will be true. A plus B over B will equal C plus D over D. Sorry, I just said you could add any number. I didn't mean that. I meant you could add the denominator. Not any number. A plus the denominator will equal C plus its denominator here. That will be true. Cool. Alright, example 1. Tell whether the following are true or false. If x over 12 equals y over 20, does x over y equal 3 over 5? Well, let's try it out here. Do our cross products. X times 20 is 20x. Y times 12 is 12y. Then is this true that when we have x over y, we get 3 over 5? So let's try to arrange this cross product to be a fraction that has x over y. So let's divide both by y. So those y's cancel. Now we get 20x over y equals 12. Let's divide that 20 on both sides. So those cancel. So now we have x over y equals 12 over 20, which we can reduce by dividing both of them by 4. So x over y equals 12 divided by 4, which is 3. And 20 divided by 4 is 5. So hey, yes! This is true. That is true. Cool. Doing great. Let's keep on cruising. Alright, question number 2 and question number 3 are just like those. So you're going to do those and show me. Awesome. Excellent. Number 4, in the figure on the right, AB, so like that side, over BD, like that side, is equal to AC over CE. Tells us that AB is 60, AE, the whole thing, is 100, and CE is 25. Well, that's not a 5. That was a 7. There we go. Because I was thinking about the next thing I was about to say. If this whole thing is 100, and that little chunk is 25, what do we know about AC? Oh yes, we know that it is 100 minus 25, which is 75. Fabulous. Now I think we have all the information we need to fill this out and solve for BD. So we had AB over BD equals AC over CE. So AB is 60, BD is the thing we don't know, equals AC is 75, and CE is 25. And you're going to finish that for me and solve, because you are totally cool with doing that. Alright, you're also going to finish those too. I have a lot of confidence in you guys in these notes. You know, I really do. You're smart cookies. And I should give you the opportunity to show me your smart cookiness. So we're going to move on as a family to the geometric mean. Now the geometric mean of two positive numbers a and b is the positive number x, such that this relationship is true. A over x equals x over b. A over x equals x over b. So it's called a geometric mean. Remember, the means are the numbers in the middle here. So if we think about this, and we solved this ratio by doing our cross product, we do a times b equals x times x. So we'd get, I'm going to flip this around because I like the x's to be on the left. X times x is x squared. A times b is just ab. If we wanted to solve for x, we need to get rid of that square root. So we'd go, so we'd get x equals the square root of ab. X equals the square root of ab. That's where that comes from. All right, some examples here. Find the geometric mean between 4 and 25. Okay, so we're finding that x value. Setting it up like 4 over x equals x over 25. Let's do a little solvey, mathy. Cross product action. 4 times 25 equals x times x. 4 times 25, of course, is 100. X times x is, of course, x squared. And then we go squirt. So x equals 10. Yeah, baby. So cool. So cool. 12 is the geometric mean between 8 and what other number? So 8 over 12 equals 12 over what other number? You're going to solve that question for me and get all your points. You guys are getting all the points on these notes for solving the problems. Okay, moving on back. Boom, shakalaka, boom, a shakalaka. Proportions are very useful in real life, for sure. Companies often create scale models of their products before constructing larger models. Why would they do that? Large models are expensive, so you want to make a tiny model where you don't use too many things, and then you'll scale it up to a bigger model. If it's cool. Otherwise, you'll make changes to your tiny model, and then you'll scale it up to your bigger model. And then you'll make the real thing. So cool. So very, very cool. All right, I'm going to help you with example 1, and then you're going to do 2 and 3. You're going to do them 2 and 3s. Example 1, an engineer makes model cars so that his 3-inch model represents an 8-foot long car. What ratio of model to car does he use? So let's look at the model over the car. The model is 3 inches. The car is 8 feet. Those are not the same units, so we're going to do some unit conversion. And we know there are 12 inches in a foot. And we want the feet to cancel, so we'll put the 1 foot on top and the 12 inches on the bottom. Our feet go bye-bye. Our inches go bye-bye. We have no more units, which is what we want. Multiply straight across, and we get 3 over 8 times 12 is 96. And then we can divide both of these numbers by 3, and we get 1 over 32. So his model to car ratio is 1 to 32. Cool. Use the ratio from part A to find the height of the model if the car is 5 feet tall. All right. So our ratio, it's still model to car. 1 to 32 is going to be equal to the car height is 5 feet. So the model height is what we are solving for. Cross product, 1 times 5 is 5. X times 32 is 32x. Divide by 32. Divide by 32. So x, excuse me, is 5 over 32 feet tall, which is, let's think about it. Half a foot would be 16 feet. A quarter of a foot would be 8 feet. So it's a little bit smaller than a 16th of a foot. Is that right? That was our model of the car. Height of the model over height of the car. Yeah, it's tiny. He's making a tiny thing. I mean, yeah, it's tiny. His 3-inch model is a foot long, so it's only going to be, it's 3 inches long. The car's going to be pretty tiny. There you go. Cool, cool, cool. All right, you got the rest of them. Love you, scholars. You're a bunch of geniuses. I'll see you next time.